Do you think Kenya could have a transparent, verifiable, and mathematically provable election? Ladies and gentlemen, my name is Edwin Kirem Kinodia, a full-stack developer, AI engineer, machine learning expert, and a former med student from the UOL. Up to this point, all our elections have always seemed to have a black box, and we cannot track the votes or verify by ourselves that the elections were transparent, free, and fair. Kenya held its last general election in 2022. About 14 million votes were cast, and once again, the results were disputed. Petitions were filed, judges deliberated, but here is the honest truth. Nobody could fully verify what actually happened inside those tallying rooms. What if an election was a computer program, and anyone on earth could read the source code, run the math themselves, and confirm the results without trusting a single person? This is what I built. This is VeriVote Kenya. So, what is VeriVote Kenya? VeriVote Kenya is a fully open source, end-to-end verifiable digital election system built specifically for Kenya. Every single vote is encrypted using real cryptography the moment it is cast, 2 anonymized through a mixing network before tallying, 3 tallied without ever decrypting individual ballots, 4 anchored to the blockchain so no one can alter the record, and 5 the final result is mathematically provable. No trust required, just mathematics. Project is fully open source under the APGL version 3 license. Every line of code you are about to see is on GitHub. The link is in the description. If you are a developer, a mathematician, or just a Kenyan citizen who wants transparent election, then this video is for you. Let me quickly walk you through what the system is made of. The backend is Node.js in TypeScript using Express and Prisma connected to a Postgres database. The frontend is Next.js 15 with Tailwind. The smart contracts are Solidity deployed on Ethereum-compatible chains. Currently on a local hard node for development. Later, we will deploy in the Polygon chain. The AI fraud detection service is Python Fast API, running a machine learning model called Isolation Forest, with the Llama 3.2 running locally via Olama. No data leaves Kenya. No cloud API. All are completely on-premise. And all of these, KYC, voting, tallying, and AI are protected by real cryptography that I am going to show you now. To fully understand this system, I'll have to explain to you what is a soul-bound token, a type of smart contract that I use to represent the voter. This kind of tech is what Binance used in the creation of Binance account on token after passage of KYC. For the sharp boys, I know you understand this. Before a Kenyan citizen can vote, they must be registered. In this system, registration creates something permanent on the blockchain, a soul-bound token, or simply an SBT. Think of it as a digital identity card that lives on-chain. Unlike a normal NFT, it cannot be transferred, it cannot be sold. It is permanently bound to one wallet, which simply translates to one voter. As you can see from my source code, the moment KYC passes and the IABC approves, this line runs. It calls our Solidity smart contract and means an untransferable token to the voter's wallet. Now, Edwin, what happens if a registered voter dies before the election? So this is what happens. An IEBC officer marks the voter as deceased in the system. The system calls the SBT revoke function on the smart contract, which permanently bans the token on-chain. Authentication is blocked forever. A dead voter, unlike in other legacy systems, cannot vote, ever. The transfer function in the Solidity contract are disabled at the code level. Any transfer from call is simply reverted. In this system, login uses web authentication, the same standard that powers fingerprint login on your phone or Face ID on a laptop. There are no passwords, there are no SMS codes that you can intercept. The voter's biometric is verified directly on their device. Nothing leaves their device. But here is the part I'm most proud of: coercion resistance. What if somebody forces a voter to vote for a specific candidate while watching over their shoulder? To cap this, every voter has two pins: a normal pin that is entered freely and a distress pin only entered when under duress. To the coercer watching, both pins look identical. The vote appears to go through successfully. The screen shows a confirmation, but silently on the server side, a flag is set. An alert is dispatched to the IEBC security, and personnel are dispatched to that polling station so that the voter can revote. Here again is my source code. Notice that pin valid becomes true for both normal and distress pin. The response back to the voter's screen is identical either way. Only its distress vote differs, and that is never sent to the client. And now, the most important part: how a vote is encrypted. We use an asymmetric cryptography scheme called ElGamal, operating on a 2048-bit prime field defined in RFC 7919. Using this, even the most powerful supercomputer would need at least 1 year to decrypt the votes. Before the election, a key pair is generated. The private key X stays offline and is split across multiple key holders. I'm going to explain this later. The public key H equals G to the power of X modulo P. So when a voter casts their vote, a fresh random number R is generated, unique to their vote only. C1 equals to G to the power of R, and C2 equals the vote multiplied by H to the power of R. So what is stored in the database? Only C1 and C2, two opaque numbers. The actual vote is unrecoverable without the private key. So if a hacker gets an unauthorized access to the database, they only see the ciphertext. Once again, here is my source code. As you can see, the current implementation uses AES 256 GCM for arbitrary ballot sizes, with the AES key itself derived from ElGamal private key via SHA-256. This means the symmetric security is tied to the same cryptographic root. Version 1 is pure ElGamal. It's also supported for legacy ballots. You can see both paths in the decrypt vote method. Let me explain to you how we are gonna tally all the votes in this system, because here it's where it gets mathematically beautiful. 1 million votes, all encrypted, and how do you count them without decrypting even a single ballot? So, ElGamal has this property called homomorphic addition. Encrypting A, then encrypting B, then multiplying the ciphertext give you the encryption of A plus B. Written formally, encryption of A times encryption of B equals encryption of A plus B. So, to tally, you multiply all the C1s together and all the C2s together, and you get an aggregate ciphertext. You decrypt it exactly once, and the result is the total vote count for every candidate. More so, we decrypt the votes once because we know during transmission is where the ballots get vulnerable, especially in legacy systems such as those using the Form 34A. As you can see from my code here, the tally results include the winner, the vote percentages, a station-by-station breakdown, a count of distress flagged votes, a reconciliation against printed paper ballot receipts, and a SHA-256 hash of the entire result, which is anchored on the blockchain. So anybody can take this hash and verify it by themselves. As promised during the ElGamal encryption, I'm gonna explain to you how we handle the private key X. The one question is, who holds this private key? If a single person holds it, they can decrypt all the votes. That is a single point of failure and a single point of corruption. In this system, we are going to use Shamir secret sharing, a mathematical scheme invented by Adi Shamir in 1979. The private key is split into shares, let's say 5. Only 3 of the 5 key holders are reconstructed, but 2 of 5 or 1 of 5 gives you nothing, mathematically nothing, not a partial key, just nothing. These 5 shares go to the 7 independent commissioners. For other types of elections supported by the system, the key goes to the top officials. To run the decryption ceremony, the 3 random officials with key must physically show up and submit their shares at the same time. No single person can ever run the tally alone. So this is the ceremony. The key shatters. 5 pieces, 7 officials, but 3 required. As such, mathematics enforces what laws alone cannot. Even with perfect cryptography, you can have fraud at human level, unusual voting patterns that no single observer would notice. The electronic voting system has an AI service that monitors every polling station in real time. It uses a machine learning algorithm called isolation forest, an unsupervised machine learning model that detects anomalies without needing labeled training data. If a station in Nairobi suddenly shows a spike in votes 3 times higher than similar stations in the same county, the model flags it, scores it, and sends an alert. The explanation is generated by Llama 3.2, a large language model running locally on our own hardware. No API call to the OpenAI, no data sent outside Kenya. The AI runs on-premise. Here, this score, 87 out of 100, is the anomaly score. Anything above 70 triggers an investigation alert. The Llama model explains in plain English why this station looks suspicious. This entire system is open source with an APGL version 3 license. That means if any government or company forks this project and deploys a modified version, they are legally required to publish their changes. No silent backdoors and no closed forks. However, I need your help to take this further. Right now, I'm a single developer, and there are real costs to making this production ready, including number 1, hosting infrastructures like servers, load balancers, and CDNs. Number 2, APIs. The Persona KYC API for real document verification currently costs money at production scale. The Africa's Talking SMS API for OTP delivery to Kenyan numbers needs some cost. And 3, the biggest one, we need a GPU. Right now, we use Persona's API to verify ID documents, but my vision is to train our own AI model on Kenyan documents, national ID, passports, and birth certificates. A model that understands Kenyan document formats exactly, runs entirely on premise, costs nothing per verification, and never sends a Kenyan citizen ID photo to a foreign server. For that, we need a GPU, and that requires funding. Here is how you can help. If you are a developer, go to the GitHub link in the description. Read the contributing.md file, click an open issue, submit a pull request, and every contribution, no matter how small, moves this forward. The areas we need most help right now are front-end UI improvement and accessibility, writing more tests for cryptographic services, Docker production deployment configuration, and also if you have machine learning experience, the ID document AI model is the most impactful thing you could work on. If you are not a developer but you believe in this, share this video. The more visibility this gets, the more contributors we attract. And if you are able to support financially, even a small contribution towards hosting or API cost keeps this project alive. I've put a till number in the description. Kenya deserves elections that cannot be stolen, not because we trust the people counting, but because the math makes it impossible to cheat. The code is here, the cryptography is is real. All we need is a community to build it together. And once again, I'm Edwin. This is VeriVote Kenya. The link to my profile is in the description below. See you in the pull request, and I hope ukokadi.
Tena utambia mam nini backbencher na mkata kakwencha ni supu tunachemsha mabit tunageuza na mistari zako bado zinaweza geuzwa. Ni serious, pigia Joffrey Musiria na pack partner nike fast kwa mkia. Niko na idea si beef bandia nikidrop wanasikia kulia. Hata sina mambo sezi kumalizia career. Wanakuhitaji watia jona kusikia siwe ni bad acha tuongezee gear. Creative kwa mic, mzoefu kwa mic. Insight zinapanda numbers don't lie. MR kwa nini cash ati foot on the gas pedal fast and furious. Nigenje sana niko neza uliza Julius. Stone festa to check it tuko serious. It's in my head but they can't bully us. Flow mysterious, sao ni hilarious. My small fish na waweka kwa aquarium. I got buzz, hard buzz kama titanium.
One day for the thief, every day for me. I go smoke so many, drink so many. Hey, jiggy, yes, so I go CBD. Eat the last body. This money go check ma. Money long. But in a day use money for all of for no serious. I take a sign anyone. Milli. How much for my Lulu with his socks? 170 milli. Jesus, yo, did with my head. Scatter my enemies, confuse them, we lead to this. Jesus, yo, I'm making wrong decisions. Anytime I see Kevin, there's all. Now two people, something she carry from waist. There's all. Now two people, something she carry from waist. Me, I know they grip play with my money. The way you collect it from me, I want to romance your body. All of our romance solo. Oh my I will spray you in dollar. Throw your back to send. Now you swear big, now in big bill. Ikebe, oh, now you swear really, now in big bill. Ikebe, take it for the sake, you're so Ikebe, where take his ass in, I still Ikebe. Jesus, yo, did with my head. Scatter my enemies, confuse them, really to this. Jesus, yo, I'm making wrong decisions. Anytime I see Kevin, there's all. Now two people, something she carry from waist. There's all, no. Now two people, something she carry from waist. There's all. You're crazy, you know.